Imagine standing outside on a quiet night and looking up at the planets, as if they are fixed decorations on a black ceiling. Jupiter is where it should be. Saturn is where the charts say it should be. Mars returns to the sky again and again, like an old signal. The moon rises. The sun will rise after it. Everything feels arranged. Everything feels locked into place. And because the solar system has been here for billions of years, it is easy to believe it will stay safe for billions more. But the frightening part is that the solar system is not a machine with unbreakable gears. It is a moving crowd of planets, moons, asteroids, comets, dust, radiation, ice, magnetic storms, hidden reservoirs, and invisible gravity. Every object pulls on every other object. Every orbit carries tiny errors forward. Every distant star that passes near the sun can disturb the outer darkness. Every asteroid that seems harmless can be changed by sunlight, by collisions, by planetary gravity, or by time. And even the sun itself, the object that makes this whole system possible, is slowly changing in a direction that no planet can stop. The solar system feels safe because we live inside one quiet moment of it. Not the beginning, not the end, a moment. And in that moment, Earth has a stable orbit, liquid oceans, a thick atmosphere, a protective magnetic field, and a star calm enough to let life build cities. But if you stretch the timeline forward, the calm begins to look less permanent. The planets are stable on human time. They are stable on the timescale of history. They may even be stable for ages longer than civilization has existed. Yet stable does not mean untouched, frozen, or guaranteed forever. Before we begin tonight's journey, subscribe to the channel if you want more calm space documentaries like this. Leave a like if you enjoy slow journeys through the universe, and write in the comments where you are watching from and what time it is where you are right now. It is always strange to think that people are listening from different parts of one small planet, at different hours, under the same solar system. Tonight, you are watching the Just About Space channel, talking about why the solar system may not be safe forever. And the first thing to understand is that danger does not always arrive as an explosion. Sometimes it arrives as a number too small to notice, a tiny change in an orbit, a slow brightening of a star, a comet nudged from a frozen shell so far away that sunlight is almost only a memory, a planet pulling another planet by a little more than expected, a solar storm launched from the sun before anyone knows whether Earth is in the line of fire. From the surface of Earth, the solar system looks familiar, but from above the plane of the planets, it looks like a thin, moving disk around a star that is not isolated at all. The sun is not sitting still in a private room. It is orbiting the center of the Milky Way. It is passing through changing regions of interstellar gas and dust. Other stars pass nearby on million-year timescales. The galaxy itself tugs on the outermost comets. The planets keep pulling on each other in patterns that are predictable for a while, then less certain when the numbers are stretched too far. This is the first terrifying truth. The solar system is safe only because many different dangers are quiet at the same time. To see why that matters, begin with the simplest part of the picture: the planets. They look permanent because their paths are so regular. Earth takes 1 year to orbit the sun. Jupiter takes almost 12. Saturn takes nearly 30. These cycles are so dependable that ancient civilizations used them to build calendars, myths, navigation, and predictions. A planet returning to the sky feels like proof of order. When Mars brightens again, when Venus becomes the evening star, when Saturn slowly drifts against the background constellations, the pattern seems almost eternal. But an orbit is not a track. There are no rails under Earth. There is no groove carved into space that forces Jupiter to stay exactly where it is. Each planet is falling around the sun while also being pulled, very slightly, by the others. Most of the time, those pulls average out. A planet is tugged one way, then another. Then the pattern repeats. The solar system survives because the large planets are separated enough and because the present arrangement has avoided disaster for a very long time. But a gravitational system with many bodies is not simple. It is not like one moon around one planet or one planet around one star. It is a crowded calculation that never ends. For the next few thousand years, the planets can be predicted with remarkable precision. Spacecraft rely on that precision. We can send probes to Jupiter, Saturn, Pluto, asteroids, and comets because the main motions of the solar system are known very well over useful timescales. But if you ask for the exact position of planets millions or billions of years from now, uncertainty grows. Tiny differences in starting conditions spread into larger differences. This does not mean Earth will suddenly fly away tomorrow. It means the solar system is not perfectly clockwork when treated across deep time. The word for that is chaos. Chaos in this sense does not mean random behavior without rules. It means the rules are real, but small uncertainties can grow. Imagine trying to predict the exact path of a leaf in a river. The water follows physics. The leaf follows physics. Nothing magical happens. Yet after enough turns, ripples, stones, and currents, a tiny difference at the beginning can place the leaf somewhere else entirely downstream. Planetary orbits are far more stable than a leaf in water, but the same kind of sensitivity exists when time becomes enormous. And the most uncomfortable example in our own solar system may be Mercury. Mercury is small, close to the Sun, and easy to ignore. It is not the planet most people imagine when they think about the future of Earth. Jupiter feels important. Mars feels close. Saturn looks dramatic. But Mercury sits deep inside the Sun's gravity well, racing around the star in only 88 Earth days. It also feels the distant influence of Venus, Earth, and especially Jupiter through long-term gravitational rhythms. Over very long timescales, Mercury's orbit can become more stretched. Its path around the Sun is already the most eccentric of the major planets. If that eccentricity grows too much, Mercury could begin crossing dangerous gravitational territory. In some simulations, Mercury's future remains calm. In others, the inner solar system becomes more unstable. The frightening part is not that a Mercury disaster is expected soon. It is that the inner solar system contains a small doorway into chaos, and the doorway is not completely imaginary. A change in Mercury would not stay politely on Mercury. If its orbit became strongly distorted, it could have close encounters with Venus, or even fall into the Sun. In the worst, long-term scenarios, disturbances could spread into the orbits of the inner planets. Venus, Earth, and Mars would not necessarily remain untouched spectators. The architecture that feels so solid could become a gravitational traffic problem, with planets exchanging energy in ways that are impossible to experience from the ground, until the consequences have already been building for ages. This is not a warning for this century, or the next one, or even the next million years in any ordinary sense. The immediate solar system is stable enough for human life, for civilization, and for exploration. The point is deeper than panic. The point is that permanence is an illusion created by short lives. A human lifetime is too brief to see planets drift from their long-term patterns. Even recorded history is too short. The entire story of agriculture, cities, empires, telescopes, satellites, and rockets is only a thin scratch on the timeline of the solar system. When something has not changed in that tiny window, we call it stable. The universe may call it temporary. The same lesson appears in the asteroid belt. Between Mars and Jupiter lies a wide region filled with rocky bodies. that never became a planet. At first glance, the asteroid belt seems like a ring of debris sitting calmly in place. Movies often imagine it as a dense field of rocks, but in reality it is mostly empty. Spacecraft cross it safely. The distances between objects are enormous, yet the belt is not a dead museum. It is shaped by gravity, collisions, sunlight, and resonance. Jupiter is the great sculptor there. Its gravity creates zones where asteroids cannot remain easily. Some orbital periods line up with Jupiter in repeating patterns. An asteroid in one of these resonant regions receives small gravitational kicks over and over again. A single kick may not matter. Millions of kicks can change an orbit. That is why the asteroid belt contains gaps, families, and pathways. Some objects are pushed into orbits that eventually bring them closer to Mars, Earth, Venus, or the Sun. This matters because Earth does not need the whole solar system to become unstable in order to face danger. One rock is enough. A large asteroid does not have to destroy the planet to change the surface of the planet. It only has to strike with enough energy to alter climate, oceans, ecosystems, and human systems. The solar system contains many small bodies, whose paths are not as simple as the major planets. Some are found early, some are dark. Some approach from directions that are difficult to watch. Some are small enough to hide until they are close, yet large enough to cause regional devastation if they hit the wrong place. This is why planetary defense exists. It is not because the sky is full of immediate doom. It is because the solar system is an active environment. Near-Earth objects attract because a small fraction of them deserve attention. Surveys search for asteroids and comets whose orbits come close to Earth's path. A potentially hazardous asteroid is not a prediction of impact. It is a flag that says, this object is large enough and close enough to deserve careful monitoring. That distinction is important. Most near-Earth objects do not threaten Earth. Many pass safely by. Some are discovered, measured, named, and watched for decades. But the reason scientists care is that small changes add up. The exact path of an asteroid depends on gravity from planets, sunlight heating its surface, the way it rotates, and sometimes the history of collisions it has survived. Even an object that misses Earth by a wide distance can have its future path changed slightly by the planet's gravity. The next encounter may be different. The encounter after that may be different again. The solar system is not a shooting gallery where every rock aims at Earth. It is also not a locked vault where every rock stays harmless forever. That is the uncomfortable middle ground. The DART mission proved that humans can change the orbit of a small asteroid by hitting it with a spacecraft. That was a real planetary defense demonstration, not science fiction. The target was not dangerous to Earth. The value of the mission was the test itself. If a dangerous object were found early enough, a kinetic impactor might slightly change its path so that Earth and the object arrive at the crossing point at different times. The technique depends on warning time, accurate tracking, and knowing how the target responds. A rubble pile asteroid, a solid rock, a binary asteroid system, or a fast comet may each behave differently. This is a strange kind of safety. It is safety built not on the solar system being harmless, but on humans learning how to notice danger before it arrives. And asteroids are only the inner version of the problem. Far beyond Neptune, beyond Pluto, beyond the Kuiper Belt, the solar system fades into a colder and less visible structure. This is where the idea of a safe solar system becomes harder to hold in your mind. The planets occupy a relatively small region around the Sun. Neptune orbits about 30 astronomical units from the Sun. Pluto's path reaches farther, but even Pluto is still close compared with the most distant objects gravitationally linked to our star. Beyond that lies the realm of long-period comets, and farther still, the Oort Cloud. The Oort Cloud is not a place anyone has photographed directly as a glowing shell. It is an inferred reservoir, a vast spherical cloud of icy bodies thought to surround the solar system at tremendous distances. These objects may be leftovers from the formation of the planets, thrown outward by the gravity of the giant worlds and kept weakly bound by the sun. They are so far away that the sun would look less like the ruler of the sky and more like a bright star among other stars. The inner solar system feels organized because we can see planets moving in a disk. The Oort Cloud is different. It may extend thousands to tens of thousands of astronomical units from the sun, perhaps even farther. At those distances, the sun's gravity is still present, but it is weak. That weakness makes the region sensitive to outside forces. Passing stars, galactic tides, and giant molecular clouds can disturb the orbits of distant icy bodies. A small nudge out there can become a long fall inward. A comet that has spent millions or billions of years in deep cold can begin traveling toward the planets. Most will never hit Earth. Many will not come close. Some will become visible only when solar heat begins waking them, producing a coma and tail as they enter the warmer parts of the solar system. But long-period comets are difficult in a special way. Unlike many asteroids whose orbits are well tracked after repeated passages, a long-period comet may arrive from the outer darkness on a path humans have never seen before. It may come in fast. It may approach from a steep angle above or below the planetary plane. Warning time can be shorter. Deflection can be harder. This is one reason the outer solar system matters to Earth's future. Earth is not protected simply because the planets are calm. The outer reservoir is part of the same system. A passing star does not need to collide with the sun to matter. It only needs to pass close enough over astronomical distances to disturb the distant comet cloud. Stars have passed near the solar system before, and more will pass in the future. Most encounters are too far to cause dramatic effects, but over billions of years, the sun moves through the galaxy, and the galaxy is full of other stars doing the same. The Oort Cloud is like a loose halo of fragile memory around the sun, and the Milky Way keeps brushing past it with gravity. The danger is not constant, it is episodic. For long stretches, nothing unusual happens. Then, a star passes closer than average, or the solar system moves through a denser region of interstellar matter, or galactic tides slowly alter the shape of comet orbits. A shower of comets is not guaranteed after every encounter, but the mechanism exists. The solar system is open to the galaxy in ways that are easy to forget when we draw it as a neat diagram on a classroom wall. Those diagrams usually end at Neptune, sometimes at Pluto, sometimes with a small label for the Kuiper Belt. But the true gravitational edge of the solar system is much larger, blurrier, and more vulnerable. If you traveled outward, you would not pass a wall that says the solar system is over. You would pass planets, dwarf planets, scattered icy bodies, the region where the solar wind gives way to interstellar space, and then an almost endless darkness of distant comets. The border is not a line, it is a fading of influence, and anything that fades can be disturbed. The heliosphere adds another layer to the story. The sun constantly blows a stream of charged particles outward. This solar wind carves a bubble around the solar system, pushing against the interstellar medium. Inside the bubble, the sun's influence dominates the local particle environment. Outside it, interstellar space takes over. Voyager 1 and Voyager 2 have crossed into interstellar space after leaving the heliosphere, giving humanity its first direct measurements beyond the sun's protective bubble. But even this shield is not fixed. The heliosphere changes with solar activity. It changes as the sun moves through different regions of the galaxy. If the interstellar environment around the solar system becomes denser or more pressurized, the shape and size of the heliosphere can change. It may compress. It may become less effective at filtering some cosmic particles. The planets would still orbit. The sun would still shine. Nothing would look like an instant catastrophe from a backyard telescope. Yet the invisible radiation environment around the planets could shift. This is one of the more subtle dangers. A dangerous solar system does not have to throw planets out of orbit. It can simply change what reaches them. Cosmic rays are high-energy particles that come from beyond the solar system, including supernova remnants and other energetic galactic sources. Earth's atmosphere and magnetic field protect the surface from much of this radiation. Astronauts, spacecraft electronics, and future settlements beyond Earth's shield face greater exposure. If the heliosphere changes, or if a nearby cosmic event increases the incoming radiation, the solar system becomes less friendly to life and technology, even if the planets remain exactly where they are. From Earth, the night sky looks still because the hazards are usually invisible. Gravity is invisible. Radiation is invisible. Orbital resonances are invisible. Long-period comets are invisible until they brighten. Interstellar gas is invisible unless instruments reveal it. The most dangerous parts of the solar system often do not announce themselves with light. They are discovered through tracking, modeling, spectroscopy, particle detectors, spacecraft measurements, and long patience. That is why the solar system can feel safe to the eye, while remaining complicated to the instruments. Then there is the sun itself. The sun is the reason Earth is alive. But it is not a permanent lamp. It is a star, and stars evolve. On human timescales, the sun feels constant. Sunrise is dependable. Seasons repeat. The amount of sunlight reaching Earth changes slightly with orbital geometry and solar cycles, but the star does not appear to be changing in a dramatic way. Yet deep inside the sun, hydrogen is being fused into helium. The core slowly changes. Over billions of years, the sun's luminosity increases. It is not racing toward tomorrow's disaster. It is moving along the long path of stellar evolution. This slow brightening matters more than it sounds. Earth sits in a delicate thermal balance. Too little sunlight, and global ice becomes a major threat. Too much sunlight, and the water cycle begins changing in dangerous ways. A warmer sun can increase evaporation, change clouds, alter weathering, affect carbon dioxide levels, and push the planet toward conditions where oceans become less stable over geological time. Long before the sun becomes a red giant, Earth can become less habitable simply because the star that sustains it becomes brighter. This is not the cinematic end of Earth. It is slower and more unsettling. The oceans do not have to boil away in one day. The sky does not have to catch fire. Habitability can erode. The comfortable range that allowed complex life to flourish can move. Eventually, if the process continues, Earth may lose the conditions that make the surface friendly to oceans, plants, animals, and humans. The solar system would still look orderly. Earth would continue its path around the sun, but safety would be gone from the only world that ever made us. This is a different kind of danger from asteroid impacts. An impact is sudden. Solar evolution is patient. One hits like a hammer, the other changes the room until no one can live inside it. In the far future, the sun will leave its main sequence stage and expand into a red giant. That future is billions of years away, but it is not optional in the physics of stars like the sun. The inner solar system will be transformed. Mercury and Venus are expected to face extreme destruction. Earth's fate depends on complex interactions involving mass loss from the sun, orbital expansion, drag in the outer solar atmosphere, and tidal forces. Even if Earth avoids being swallowed, it will not remain Earth as we know it. Its oceans and life-friendly surface will be gone long before that final red giant drama. The frightening lesson is simple. The solar system is not designed for life. Life found a temporary window inside it. That window can be very long and still not be permanent. The planets formed from a disk around a young star. They were not placed into their current arrangement for human comfort. Earth became habitable because chemistry, distance, mass, atmosphere, magnetic field, water delivery, and time happened to combine in a way that worked. Mars was once wetter than it is now. Venus may have followed a very different path, into a runaway greenhouse. Mercury was baked and stripped. The outer moons preserve ice, oceans, radiation scars, and deep cold. Habitability in the solar system is not a default condition. It is rare, local, and fragile. Even Earth is protected by systems that can fail or change. The magnetic field shields the planet from much of the solar wind. The atmosphere absorbs harmful radiation and moderates temperature. The ozone layer protects the surface from dangerous ultraviolet light. Plate tectonics helps regulate carbon over long periods. The moon stabilizes Earth's axial tilt, compared with what it might otherwise do. Jupiter helps shape comet and asteroid traffic, sometimes deflecting objects, sometimes redirecting them. Every layer of safety is a process, not a wall. Processes can weaken. Processes can change. Processes can be overwhelmed. Solar storms show how even the present sun can remind us that safety is conditional. A solar flare or coronal mass ejection does not threaten Earth the way a giant asteroid does. It does not punch a crater into the ground. But a powerful geomagnetic storm can disturb satellites, radio communication, navigation systems, electrical grids, and spacecraft. In a world dependent on technology, an event in the sun's atmosphere can become an event in human civilization. The solar system may be safe for bodies walking on the ground, while becoming dangerous for the invisible networks those bodies depend on. The Carrington event in the 19th century is often used as a warning example because it occurred before the modern electrical world. Telegraph systems were affected. Auroras were seen unusually far from the poles. If a similar or stronger storm struck today's technology-dependent Earth, the consequences would be different because the target has changed. We have satellites, high-voltage grids, GPS, aviation routes, internet infrastructure, and spacecraft. The sun has not become more malicious. Civilization has become more exposed. This turns the meaning of solar system danger upside down. The environment can remain the same while our vulnerability grows. A storm that once produced strange lights and damaged telegraph lines could now affect navigation, banking, communication, weather forecasting, and emergency response. A modest change in solar behavior, combined with a deeply connected civilization, can become a global problem. The solar system does not need to change drastically to stop feeling safe. Sometimes we change first. The same is true for space exploration. As long as humanity lived only on Earth's surface, many solar system hazards were distant curiosities. Radiation belts mattered to instruments and satellites. Lunar dust mattered to astronauts for a few days. Martian dust storms mattered mostly to rovers. Micrometeoroids mattered to spacecraft. But if humans build bases on the Moon, Mars, asteroids, or in orbit, the danger map expands. A region that was safely ignored from Earth becomes a place where people must live. The Moon is not protected by a thick atmosphere. Mars has a thin atmosphere and no global magnetic field like Earth's. Asteroids have almost no gravity, no air, and no forgiving environment. Deep space habitats would rely completely on machines. In that future, the solar system may not be unsafe because Earth is immediately threatened. It may be unsafe because humans begin living in places where the system has always been hostile. The solar system was never built as a collection of future homes. It is a collection of worlds, most of them lethal without technology. Colonization would not make the solar system safe. It would place fragile human systems into a dangerous environment and ask them to keep working for decades, centuries, or longer. That is why the question is larger than one asteroid, one solar storm, or one distant comet. The real question is whether the solar system is stable enough for a civilization that wants to last. Not for a lifetime, not for a mission, for geological time. A civilization that lasts thousands of years can survive ordinary storms, impacts, and climate challenges if it is wise and prepared. A civilization that lasts millions of years has to think differently. It must track asteroids continuously. It must understand solar cycles. It must survive volcanic winters, climate shifts, cometary risks, and technological fragility. It must eventually face the changing sun. It must decide whether to remain on Earth, move outward, build habitats, alter planets, or leave the solar system entirely. The solar system becomes a test of patience. Short-term safety asks, can we survive this century? Long-term safety asks, can we survive the star? Between those two questions are many smaller ones. Can we detect dangerous asteroids early enough? Can we deflect them without creating new hazards? Can we harden electrical grids against solar storms? Can we protect astronauts from radiation? Can we build life support systems that do not fail quietly? Can we use the resources of the Moon, Mars, and asteroids without trapping ourselves in fragile outposts? Can we predict which dangers are real and which only sound dramatic? The frightening part is that each problem has a different clock. Asteroids can be sudden on human timescales. Solar storms can arrive with hours to days of warning after an eruption is detected. Long-period comets may give months, maybe years, but not always the comfortable notice planners would want. Planetary chaos lives on timescales so long that it is easy to dismiss. The sun's aging unfolds across billions of years, so slowly that no one alive can feel it. A close stellar encounter may matter over hundreds of thousands or millions of years. Because the clocks are different, the danger feels unreal. Humans are good at reacting to footsteps behind them. We are less good at responding to a comet reservoir disturbed by a passing star, or a star that becomes gradually brighter over a timescale longer than our species has existed. The solar system's future is not one countdown. It is a room full of clocks, each ticking at a different speed. Some loud, some nearly silent. That is why calling the solar system safe can be misleading. It is safe now, in the narrow sense, that the planets are not colliding. No known large asteroid is on a confirmed short-term impact path with Earth, and the Sun is not about to become a red giant. But safe forever is a much stronger claim. Forever reaches into orbital chaos, stellar evolution, cosmic encounters, and human expansion. Forever asks whether a system shaped by gravity, radiation, ice, dust, and nuclear fusion will remain friendly to life indefinitely. The answer is no, not in the way we wish. The solar system can protect life for a while. It can host oceans, weather, sunlight, and evolution. It can give a species enough time to look around and understand its situation. But it cannot promise that the arrangement will last. The sun will change. Small bodies will keep moving. The outer cloud will keep feeling the galaxy. The planets will keep exchanging tiny gravitational whispers. Human technology will keep becoming both stronger and more dependent on invisible systems. And that brings us to the next level of danger. The threats that do not come from inside the solar system, but still reach into it. A nearby supernova, a passing star, a dense interstellar cloud. The slow motion of the sun through the Milky Way. These are not everyday threats. They are not reasons to fear the sky tonight, but they reveal something important. The solar system is not sealed away from the galaxy. It is moving through it. And as soon as you understand that, the safe little diagram of planets around the sun begins to feel much smaller. The galaxy is not a background. It is an environment. And the solar system is traveling through that environment right now. To understand why that matters, imagine the Sun not as the center of a perfect cosmic island, but as a ship crossing a vast ocean. The planets move with it. The Oort Cloud trails around it like an enormous swarm of frozen debris. The heliosphere forms a shifting bubble around it. Earth rides deep inside, protected by layers of gravity, atmosphere, magnetism, and distance. For now, the ocean is calm enough. But oceans have weather. The galactic ocean has weather too. Not rain, wind, and waves in the ordinary sense, but star fields, radiation sources, molecular clouds, supernova remnants, density variations, and gravitational encounters. The Sun's path around the Milky Way takes hundreds of millions of years. During each orbit, it does not pass through the exact same surroundings in the exact same way. The galaxy is structured. It has spiral arms, gas clouds, star-forming regions, and old stellar populations. The solar system is part of that flow. This does not mean every passage through a spiral arm is a guaranteed disaster. The science is not that simple. But it does mean our local environment can change. The solar system's outer boundary, comet reservoirs, and incoming radiation are not isolated from galactic conditions. A nearby supernova could increase cosmic ray flux. A close star could disturb the Oort cloud. A denser interstellar cloud could alter the heliosphere. These possibilities are rare on human timescales, but deep time makes rare events less rare. And deep time is the only honest way to talk about forever. One of the most dramatic external threats is a supernova close enough to matter. Most supernovae are far away. They are beautiful through telescopes and harmless to Earth. A massive star explodes, shines with incredible energy, enriches space with heavy elements, and leaves behind a neutron star or black hole. The blast wave expands into interstellar space. Radiation spreads outward at the speed of light. Cosmic rays can follow. If the event is distant, it is part of the galaxy's normal life cycle. If it is close enough, it becomes part of Earth's environmental story. A dangerous nearby supernova would not need to crack the planet open. It could affect the atmosphere. High-energy radiation and cosmic rays might damage the ozone layer, increase surface ultraviolet exposure, and influence climate chemistry. The exact effects would depend on distance, direction, energy, and Earth's conditions at the time. Again, the threat is not that a known nearby star is about to explode in a way that will certainly harm us tomorrow. The lesson is broader. The solar system's safety includes what happens beyond Neptune, beyond the Oort cloud, and beyond the Sun's own neighborhood. The most famous nearby red supergiant Betelgeuse is often mentioned in public discussions because it will explode someday. But it is far enough away that it is not considered a serious threat to Earth when it does. The more important idea is not one celebrity star. It is that stars die throughout the galaxy, and the solar system's long-term history includes the possibility of being close to energetic events at some point across vast timescales. Space is mostly empty, but mostly empty is not the same as perfectly safe. A galaxy is a place where stars are born, age, explode, pass near each other, and shape the environments around them. Earth is protected from most of that by distance. Distance is one of our greatest shields. Yet distance is not a law that says nothing can ever come close. The Sun moves, other stars move. Over time, the neighborhood changes. This is why the future solar system must be seen as dynamic. The planets are not sitting inside a glass display case. They are being carried through a galaxy that continues to evolve. And then, there is the problem of Jupiter. Jupiter is often described as Earth's protector, and there is truth inside that idea. Its enormous gravity shapes the asteroid belt, captures or redirects objects, and influences comet paths. Without Jupiter, The history of impacts in the inner solar system might be very different. But Jupiter is not simply a shield. It is also a gravitational engine. It can remove objects from dangerous paths, and it can place some objects onto dangerous paths. A giant planet does not make a small body system quiet. It organizes the chaos into channels. This is why the phrase "Jupiter protects Earth" can be too simple. The real Jupiter is more complicated. It has swallowed comets. It has been struck by fragments, as happened with comet Shoemaker-Levy 9 in 1994. It sends gravitational influence across the asteroid belt. It participates in resonances. It helps define which orbits are stable and which are unstable. It may reduce some risks while increasing others. Its importance is not only that it blocks danger, its importance is that it controls traffic. The inner solar system lives downstream of that traffic. A small object can be shifted inward by interactions with giant planets. A comet can have its orbit shortened. An asteroid can drift into a resonance. A family of fragments can spread after a collision. A near-Earth object can be influenced by repeated planetary encounters. Over time, the population of hazards changes. The rocks and ice do not stay neatly categorized forever. This is one reason planetary defense cannot be a one-time project. You cannot survey the sky once and declare the solar system safe forever. New objects are discovered. Orbits are refined. Small changes accumulate. Instruments improve. The list of known objects grows. The risk picture becomes clearer, but never finished. It is more like weather monitoring than map making. The map is real, but the system keeps moving. This is also why the solar system's future can feel so unsettling. The dangers are not all dramatic enough for one simple story. Some are slow, some are sudden, some are local, some are galactic, some threaten life directly, some threaten technology, some threaten future colonies more than Earth. Some are so far away in time that they seem philosophical until you remember that the solar system itself is old enough for those timescales to matter. A safe system would be one where the conditions that make life possible are locked and permanent. Our system is not like that. It is survivable. It is beautiful. It is rich with stable patterns. But it is also changing. That difference matters. When people say the solar system has lasted for billions of years, they are right. But the solar system that existed after the planets formed was not identical to the one we see now. The young solar system was violent. Planets grew through collisions. Debris was scattered. Giant impacts shaped worlds. The moon likely formed from a colossal impact early in Earth's history. The surfaces of the moon, Mercury, Mars, and many moons preserve scars from heavy bombardment. The calm we see today came after a long era of clearing, migration, impacts, and rearrangement. The present peace is partly the result of past violence. Many dangerous objects were removed, swallowed, ejected, or locked into more stable reservoirs. The planets that survived are the survivors of a selection process. The orbits we trust are the orbits left after the most unstable configurations disappeared. That does not make the current system fragile in an immediate sense. It makes it historically shaped, and history never guarantees eternity. Even Earth's position is a temporary success. Too close to the sun, and water becomes unstable. Too far, and the planet can freeze. Too small, and it loses atmosphere. Too large, and its evolution would be different. Without a large moon, its axial behavior might be less stable. Without enough heavy elements, there would be no rocky planet like this at all. Without earlier generations of stars, the ingredients would not exist. The solar system is safe for us because we evolved in the part of it that worked. That sounds obvious, but it changes the emotional picture. We are not looking at a random solar system and discovering it was made safe. We are the product of the safe part of a system full of unsafe parts. We notice the calm Because the calm allowed observers to appear. A civilization on Venus never wrote a warning about runaway greenhouse conditions. A civilization on Mercury never watched sunrise from an ocean. If Mars once had surface environments more friendly to water, those conditions did not last the way Earth's did. Habitability is not a property of the whole solar system. It is a rare, local accident maintained by many moving pieces. And the first half of this journey leads to a single conclusion. The solar system may be stable, but it is not guaranteed safe forever. Not because every danger is likely tomorrow. Not because the planets are about to scatter. Not because a hidden apocalypse is waiting behind Neptune. But because every layer of safety has a clock attached to it. The asteroid clock. The comet clock. The solar storm clock. The orbital chaos clock. The stellar evolution clock. The galactic environment clock. For now, most of those clocks are quiet. Some tick slowly enough that humans barely notice. Some are watched by telescopes, spacecraft, and models. Some belong to futures so distant that only a civilization with deep patience could prepare for them. But none of them is imaginary. There is also a danger that feels almost too quiet to count: accumulation. One small impact on a spacecraft panel is not the end of civilization. One solar storm does not erase humanity. One close asteroid flyby is not disaster. One difficult drought, one satellite failure, one communication blackout, one temporary power loss, one damaged observatory, one missed launch window. None of these has to end the human story. But the solar system is an environment where stresses can layer on top of each other. A future lunar base could survive a micrometeorite strike if its compartments seal properly. It could survive a solar storm if people reach shielded shelters in time. It could survive a dust-covered radiator if spare equipment exists. It could survive a delayed cargo ship if storage was planned well. But stack those problems together, and the same base becomes fragile. A solar storm interrupts surface work. A landing delay postpones replacement parts. Dust damages seals. A micrometeorite punctures a weak section. The emergency team is tired. Communication with Earth is delayed. Suddenly, the danger is not one spectacular event. It is the combination. This is how real systems fail. Not always through a single monster, often through a chain. The solar system is full of chain risks for any civilization that spreads beyond Earth. A Mars settlement may be safe during ordinary weather, but less safe after a dust storm reduces solar power. A spacecraft may be safe while its thermal system works, but not if a coolant loop fails during a long eclipse or far from repair crews. An asteroid mining station may be safe while its rotating habitat stays balanced, but not if a mass shift changes its spin. A deep space telescope may survive radiation for years, then lose a critical component after repeated exposure. The threat is not just the environment. It is the environment plus time. Time turns small weaknesses into serious ones. On Earth, repair is normal. Supply chains surround us. A broken machine can be replaced by another machine built in another city, shipped across oceans, installed by people who breathe the air around them. In space, every repair becomes a story about distance, mass, planning, and survival. The farther humans move into the solar system, the more every small hazard becomes connected to logistics. This means the solar system may be safe for explorers, but dangerous for permanence. A short mission can carry extra supplies. A permanent settlement must make safety ordinary. That is much harder. The Moon teaches this lesson immediately. It is close to Earth compared with any other world, yet it has no breathable air, no surface water lakes, no thick atmosphere, no weather that softens impacts, and no global magnetic shield. A moon base would live in a place where the ground itself is abrasive, the sky is black at noon, and temperature changes can be extreme. It is nearby only in distance. Environmentally, it is another world entirely. Mars teaches a different lesson. It looks more Earth-like in images because it has landscapes, polar caps, clouds, dust devils, valleys, and a day length close to Earth's. But the familiar look is misleading. The air is too thin to breathe, mostly carbon dioxide, and offers limited protection from radiation. The cold is severe. Dust can cover machinery. Launch windows to Earth are controlled by orbital geometry. A problem on Mars is not solved by simply turning around and coming home. The asteroid belt teaches another version. It contains resources, but also bodies with weak gravity, irregular shapes, spinning surfaces, loose regolith, and uncertain interiors. Landing on an asteroid is not like landing on a small planet. Touching the surface can disturb material. Anchoring can be difficult. A mining operation would have to manage dust, momentum, rotation, power, and escape paths. The object being mined might not behave like a solid mountain. It might behave like a pile of fragments held together by weak gravity. Each place in the solar system offers opportunity and danger together. Water ice can support life support and fuel, but extracting it may be hard. Sunlight can provide power, but only when available and when dust or night does not interfere. Low gravity can make launches easier, but it may damage human bodies over time. Resources can reduce dependence on Earth, but only after the machines to use them are already working. This is why the future solar system may become less safe as humans become more ambitious. Not because ambition is wrong, but because every new frontier creates new failure modes. A civilization that remains only on Earth faces one set of hazards. A civilization spread across orbit, the Moon, Mars, asteroids, and outer moons faces many more environments, each with its own clock, chemistry, gravity, and radiation. And the outer moons show how strange those environments can be. Europa may hide a global ocean beneath ice, but it orbits inside Jupiter's powerful radiation environment. A probe or future base there would need shielding and careful planning. Enceladus sprays material from its south polar region, offering clues about a hidden ocean, but it is a small icy moon in the cold outer system. Titan has a thick atmosphere and organic chemistry, but its surface is far colder than any place humans naturally survive. These worlds are fascinating because they may hold clues about life, chemistry, and planetary evolution. They are not safe simply because they are interesting. The deeper humans look, the clearer the pattern becomes. The solar system contains many possible futures, but almost none of them are easy. Even the idea of moving outward to escape the warming sun is not simple. If Earth becomes less habitable in the far future, the outer solar system may receive more sunlight as the sun brightens. Icy moons could warm. Regions that are now frozen might become more active. But the timing, environment, radiation, gravity, and chemistry would still matter. A moon becoming warmer is not the same as becoming Earth. A place with ice is not automatically a place where forests grow. A world with an ocean is not automatically a home. A civilization fleeing one danger may meet another. That is why the solar system's future is not a simple migration from bad places to good places. It is a moving map. The habitable zone shifts. Resources become more or less useful. Radiation environments remain harsh. Planetary orbits continue. The sun changes. Technology has to adapt faster than environments become hostile. A safe future would require not just escape, but continuous engineering. There is another uncomfortable point. Knowledge itself has limits. We can calculate a great deal. We can model orbits, measure asteroids, observe the sun, simulate climate, track spacecraft, and study stars like our own. But the farther we project, the more uncertainties matter. A future asteroid impact risk depends on discoveries not yet made. Long-term orbital chaos depends on tiny variables. Future solar activity has patterns, but not perfect predictions. The response of a human civilization to these hazards is even harder to predict than the hazards themselves. A civilization can make the solar system safer by watching it. It can also make itself more vulnerable by ignoring what it sees. That may be the most human part of the problem. The solar system does not care whether warnings are convenient. It does not care whether a century is politically short or scientifically long. It does not care whether building planetary defense is exciting, whether grid hardening is profitable, whether deep space radiation shielding is expensive, or whether life support redundancy feels boring. The environment follows physics. Safety is something intelligent beings have to build inside that physics. And building safety is not the same as discovering that safety already exists. The solar system is often presented as our neighborhood, and that word is comforting. Neighborhoods have familiar streets, they have homes, they have repeated routes. But a cosmic neighborhood is not a suburb. It contains an active star, lethal radiation belts, airless rocks, unstable small bodies, deep cold, orbital resonances, comet reservoirs, and a future red giant. Calling it our neighborhood is emotionally true because it is where we came from. It is not physically true if the word implies comfort. A better image may be a harbor. Earth is the ship tied safely to the dock. The dock is real. The water is real. But beyond the dock is weather. For millions of years, life stayed close to the dock. It did not need to cross the harbor. It did not need to build engines, shelters, navigation systems, radiation shields, asteroid surveys, or off-world farms. Then, one species began to understand the wider harbor. It built telescopes first, then rockets, then probes, then permanent machines around other worlds. With every step outward, the harbor became less symbolic and more literal. The solar system is not becoming dangerous because humans noticed it. Humans are finally noticing how dangerous it has always been. That is an important difference. The moon did not become airless when Apollo arrived. Mars did not become cold when rovers landed. The asteroid belt did not become chaotic when astronomers mapped resonances. The Oort Cloud did not become vulnerable to passing stars because we gave it a name. The dangers were already there. Awareness simply changed our relationship with them. And awareness creates responsibility. Once a civilization knows that asteroids can be tracked, ignoring them is a choice. Once it knows that solar storms can harm infrastructure, leaving systems fragile is a choice. Once it knows that long-term habitability is not guaranteed, refusing to think beyond short-term comfort is a choice. The solar system may not be safe forever, but it can become safer for a civilization that learns to treat time as a real part of survival. That may be the most practical lesson hidden inside this enormous subject. The future is not only something that happens. Some parts of it can be prepared for. A dangerous asteroid found decades early is a very different object from one found days before impact. A solar storm forecast is more useful when power grids and satellites are designed to respond. A Mars base is less fragile when it has spare parts, buried shelters, multiple power systems, and the ability to produce essentials locally. A civilization is less trapped by the sun's future if it begins building knowledge, industry, and habitats beyond one planet long before it is forced to. The solar system does not offer safety as a gift. It offers time. Time to detect, time to understand, time to build, time to move. But time can be wasted. That is why the same system can be both generous and terrifying. Earth has had billions of years of relative stability. That stability allowed intelligence to emerge. Yet the hazards that wait beyond human attention do not disappear because the present moment is calm. A quiet century is not proof of a safe, forever. It is only a chance to prepare for the next clock that starts ringing. And the next part of the story begins, where the familiar solar system ends. In the outer darkness, where the sun's control fades, the galaxy begins to push back, and the idea of safety becomes much harder to define. Out there, the first danger is not a planet, an asteroid, or a visible wall in space. It is the loss of the sun's protection. From Earth, the sun feels like a lamp. From the outer solar system, it becomes something stranger, a wind machine, a magnetic engine, and a shield. Every second, the sun sends charged particles outward in all directions. This solar wind fills the space around the planets, sweeps past Earth, crosses the orbit of Mars, moves beyond Jupiter, reaches Saturn, Uranus, Neptune, and keeps expanding into the dark. For most of human history, we imagined the solar system as a collection of worlds orbiting in empty space. But the space between those worlds is not completely empty. It is filled with weak magnetic fields, particles, dust, plasma, and invisible streams of energy. The sun carves out a bubble inside that environment. That bubble is called the heliosphere. Inside it, the sun still matters. Outside it, the galaxy begins to matter more. This is why the edge of the solar system is not as simple as the orbit of Neptune. Neptune is only the last major planet. Pluto and the Kuiper belt stretch farther. The scattered disk reaches deeper into the cold. Far beyond that, the Oort Cloud may extend so far that distances stop feeling planetary and begin to feel interstellar. But long before the outermost comets are reached, the solar wind runs into pressure from the interstellar medium. That meeting place is the heliopause. It is not a solid border. A spacecraft does not hit it like a wall. It is more like the place where one ocean current loses strength against another. On one side, particles and magnetic fields are dominated by the sun. On the other side, the local material between stars takes over. Voyager 1 crossed that region and entered interstellar space in 2012. Voyager 2 followed later. These spacecraft did not leave the sun's gravity in the full sense. They did not pass beyond the Oort Cloud. But they did cross out of the sun's protective bubble, and what they found made the outer edge feel less like a clean boundary and more like a weather system. Cosmic rays increased. Solar particles declined. The plasma environment changed. The magnetic field behaved in ways scientists had to study carefully, because the transition was not a simple textbook line. That is the first lesson from the outer darkness. The solar system is not sealed. It has a skin, and that skin can be pressed, stretched, reshaped, and disturbed. If the sun were drifting through perfectly empty space, that bubble might seem more stable. But the sun is not alone. It is moving through the Milky Way, through thin gas, magnetic fields, old supernova debris, dust, and clouds of interstellar material. The planets are not sitting inside a permanent room. They are traveling inside a bubble carried through a changing galactic landscape. That means the solar system's level of protection is not fixed forever. It depends partly on where the sun is. Right now, the space around the sun is thin by ordinary standards. The local interstellar environment is extremely sparse, compared with anything we would call air. But the galaxy is not uniform. Some regions are emptier. Some are denser. Some contain clouds of gas and dust. Some carry the memory of exploded stars. If the solar system passes into a different environment, the heliosphere may change. A denser interstellar cloud could push harder against the solar wind. The protective bubble could shrink. More galactic cosmic rays might reach the inner solar system. The change would not look like a monster arriving in the sky. There might be no dramatic object for people to point at. It would be more subtle, a shift in radiation levels, a different pressure outside the planets, a new balance between the sun and the galaxy. The danger would come from the fact that invisible boundaries can still affect real worlds. For Earth, the atmosphere and magnetic field add another layer of protection. They do not make the planet invincible, but they reduce what reaches the surface. For astronauts, satellites, future lunar bases, Mars settlements, and deep space habitats, the heliosphere matters much more directly. A civilization spread through the solar system would not only live on planets, it would live in space between them. It would need to understand what surrounds the whole system, not just what happens near Earth. This is where the idea of safety becomes larger. A safe solar system is not only one with calm planets, it is one with a stable outer shield. But even that outer shield is not the final boundary. Far beyond the heliopause, the Sun's gravity still holds an enormous population of icy bodies. The Oort Cloud is not a photographed shell. It is inferred from the behavior of long-period comets, from theory, and from the way the solar system likely formed. If it exists as expected, it may contain countless frozen objects spread across a huge spherical region around the Sun. This region matters because it turns the solar system into a much larger and less predictable place. Near Earth, we mostly worry about asteroids whose orbits can be tracked over years, decades, or centuries. In the outer Oort Cloud, objects move so slowly and so far away that they can remain invisible until something disturbs them. A comet can spend most of its existence in darkness, barely moving from the perspective of a human lifetime. Then a small gravitational nudge can change its path. The nudge may come from the tide of the galaxy. It may come from a passing star. It may come from the long, weak pull of the Milky Way itself. Over millions of years, tiny influences matter. A star does not need to crash into the solar system to disturb it. It only has to pass close enough to tug at distant comets. The outer Oort Cloud is so loosely held by the Sun that the gravity of other stars begins to compete. At those distances, the solar system is not a private island. It is part of a gravitational neighborhood. That neighborhood changes. Stars pass the Sun. Most are extremely far away. Some pass closer. Even a close stellar encounter on astronomical scales may still be far beyond the planets, but the Oort Cloud is so vast that a passing star can shake the system's outer storage region. It can redirect icy objects. Some may be thrown away forever. Others may be sent inward. This does not mean a single passing star automatically causes disaster on Earth. The solar system is large, and most comets never hit anything important. But it does mean the outer system is not a frozen museum. It is more like a distant reservoir connected to the inner planets by gravity. A comet sent inward from the Oort Cloud can take an extremely long time to arrive. When it does arrive, it may come from an unusual angle, with a huge orbit, at high speed, and with less warning than many near-Earth asteroids. That is one of the uncomfortable things about long-period comets. They can appear from deep space with paths that were not part of our ordinary inner solar system inventory. They are not all extinction threats. Most are not. Many are beautiful visitors. But the same mechanism that makes comets beautiful also makes them difficult. A frozen body that has spent ages in the deep cold can suddenly become active when sunlight warms it. Ice turns into gas. Dust streams out. A tail grows. A silent object becomes visible. By then, it may already be well on its way toward the inner planets. This is one reason the safety of the solar system cannot be measured only by what is close today. The danger can be stored far away. The past can send objects into the future. The outer darkness can become an inner threat. There is something almost calm about that idea, and that calmness is what makes it unsettling. Nothing needs to explode. No alien force needs to appear. No planet needs to lose its orbit overnight. The solar system can remain quiet for thousands of years while slow gravitational changes are already preparing the next visitor from the edge. For a civilization like ours, this creates a problem of patience. Human beings are good at reacting to things they can see. Smoke, storms, earthquakes, wars, shortages, sickness, and sudden accidents fit the scale of our nervous system. But the solar system does not always warn us on human time. Some of its clocks are measured in centuries. Others are measured in millions of years. A real threat can begin as a tiny orbital change, too small to feel, too distant to image, and too slow to make headlines. That is why long-term safety requires a different kind of intelligence. Not panic, not prediction with perfect certainty. A patient map. The map would need to include asteroids, comets, solar activity, planetary motion, spacecraft, colonies, power systems, spare infrastructure, and the outer gravitational environment. It would need telescopes watching the sky again and again. It would need missions that study comets before they become emergencies. It would need warning systems that work when the threat is still small. Because in space, early knowledge is not just science, it is survival time. The next layer of danger comes from something even larger than the Oort Cloud, the galaxy itself. The solar system orbits the center of the Milky Way. It does not drift through a perfectly empty, perfectly quiet circle. It moves with the local stars, passes through changing environments, and remains surrounded by a galaxy that has its own structure. Spiral arms, molecular clouds, star-forming regions, supernova remnants, dark matter, and tidal forces all belong to the larger setting in which the solar system exists. From Earth, the galaxy can feel like scenery, a pale band across the night sky, a background for myths, navigation, and telescope images. But the Milky Way is not wallpaper. It is a gravitational system with hundreds of billions of stars, huge clouds of gas, streams of old stars, black holes, stellar nurseries, dead stellar cores, and invisible mass-shaping motion on enormous scales. The solar system is moving through that system whether we think about it or not. This movement is not normally dangerous in the short term. The Sun has traveled around the galaxy many times during its life, and Earth has remained habitable through most of that journey. Life has survived asteroid impacts, climate swings, ice ages, volcanic disasters, and changes in solar brightness. But survival in the past is not the same as permanent safety in the future. The galaxy contains rare events that are powerful enough to matter. Nearby supernovae are one example. A supernova is not just a bright death. It is a stellar explosion that can release enormous energy, produce heavy elements, accelerate cosmic rays, and reshape nearby space. Most supernovae are far away enough to be harmless to Earth. Some are close enough to be spectacular in the sky, but not catastrophic. But if a massive star exploded too close, its radiation and cosmic rays could affect a planet's atmosphere. The danger would not necessarily be a fireball burning the ground. Space disasters often work indirectly. High-energy radiation could damage the upper atmosphere. Cosmic rays could increase. Ozone chemistry could change. More ultraviolet light could reach the surface. The biological consequences would depend on distance, orientation, energy, atmosphere, magnetic field, and time. This is what makes the galactic environment difficult to explain with one simple sentence. It is not that the solar system is surrounded by constant doom. It is that it exists inside a universe where rare events are still real. The safer a place seems today, the easier it is to forget that rare does not mean impossible. A dangerous stellar explosion near enough to seriously affect Earth is not something we expect tomorrow. But across deep time, the galaxy keeps making massive stars, and massive stars do not live quietly. They end violently. They seed space with elements, but they also remind every nearby world that the galaxy is alive in ways planets cannot control. Then, there are gamma-ray bursts. These are among the most energetic events known. Some are connected with the collapse of massive stars or the merger of compact objects like neutron stars. They can send intense beams of radiation across space. For Earth to be seriously affected, one would need to be close enough and pointed in the right direction. That makes the threat unlikely on ordinary human timescales. But the idea is still terrifying because the signal travels at light speed. There is no slow object to deflect, no asteroid trajectory to alter, no visible approach across the sky. If a dangerous beam were already on its way from far away, the first warning would essentially arrive with the event itself. Again, this does not make daily life unsafe. It does not mean people should live in fear of the sky, but it shows the deeper point. A solar system can be stable internally and still be exposed externally. The planets can follow their orbits. The sun can shine normally. Earth can turn through ordinary days. And still, the larger galaxy can occasionally produce events that do not care how peaceful the local system looks. Safety is layered. Some layers are close, some are far. Some are slow, some are sudden. The next danger is not an impact or an explosion, but dependency. As humans imagine spreading through the solar system, it is tempting to think expansion automatically solves the problem. If Earth is vulnerable, build on the Moon. If the Moon is limited, build on Mars. If Mars is fragile, use asteroids, orbital habitats, icy moons, and free space colonies. A multi-world civilization sounds safer than a one-world civilization, and in many ways it would be. But expansion does not remove danger by itself. It changes the type of danger. A Mars city is not safe because it has red dirt under it. A lunar base is not safe because it is close to Earth. A habitat in orbit is not safe because it can move. Each place needs energy, shielding, water, food, repair capacity, medical support, knowledge, manufacturing, communication, navigation, and social stability. A settlement can be far from Earth and still depend on Earth for the parts that keep it alive. That is not true independence. It is a longer supply chain. A solar system civilization would need more than flags on different worlds. It would need redundancy. If one site fails, another must continue. If one launch system breaks, another must work. If one power source is damaged, another must take over. If a solar storm hits, the grid must not collapse everywhere at once. If a supply route closes, people must survive long enough to reopen it. The first off-world settlements may be more fragile than Earth, not less. Earth has air, oceans, soil, weather, a biosphere, a thick atmosphere, a protective magnetic field, and millions of natural processes that support life without anyone maintaining them. Mars does not. The Moon does not. Asteroids do not. A space habitat certainly does not. In those places, the difference between home and death is engineering. A cracked seal, a failed pump, a damaged radiator, a contaminated water loop, a software error in a life support system, a fire in a closed environment, a dust-covered solar farm, a medical emergency with no hospital nearby. These are not dramatic cosmic threats, but they may be the threats that matter most at first. A civilization trying to make the solar system safer may discover that the first centuries of expansion are the most dangerous ones. People would leave the natural protections of Earth before they had fully built replacements. That creates a strange middle phase, too advanced to stay only on Earth, not advanced enough to be truly secure elsewhere. In that phase, the solar system may feel larger but not safer. It may contain more human settlements, more machines, more ships, more power systems, and more possible failures. A small society on Mars could be safe from an earthquake on Earth, but vulnerable to a broken oxygen plant. A lunar base could survive a terrestrial war but be damaged by a micrometeorite or a power shortage during the long night. An asteroid mining station could have valuable material around it and still be one accident away from evacuation. This is why safety is not the same as distance. Moving away from Earth helps only if the new place can support itself. Otherwise, every colony is a dependent outpost, and every dependent outpost is another fragile point in a wider system. There is also a psychological danger hidden inside the idea of a safe solar system. People may confuse expansion with escape. They may imagine that once humanity reaches several worlds, the species problem is solved. But a multi-world civilization can still share the same vulnerabilities. If all settlements depend on the same technologies, the same supply networks, the same communication systems, the same political structures, or the same narrow sources of energy, then a single type of failure can spread through many places. A solar storm does not need to hit only Earth if satellites, navigation networks, and power systems across the inner solar system depend on vulnerable electronics. A software flaw can travel with every copied system. A bad design can become universal if everyone uses it. A political collapse can reach far through finance, trade, data, and dependence. A biological problem can become more dangerous if space habitats are small, closed, and medically limited. In other words, the solar system can be geographically wide and systemically narrow. That is a dangerous combination. True safety would require diversity, not just distance. Different habitats, different energy sources, different food systems, different archives, different governments, and different survival strategies. Some settlements would need to be able to go quiet and keep living. Others would need to be able to repair without help. Some would need to specialize in observation, others in manufacturing, others in medicine, propulsion, agriculture, and long-term storage. The solar system would need to become more like an ecosystem, not one machine stretched across many worlds, but many systems, able to support and replace one another. This is difficult because space rewards efficiency. A habitat with no wasted mass, no spare parts, and no extra power may be cheaper to build, but efficiency can be the enemy of survival. A system built only for normal conditions may fail, when the universe stops being polite. The same is true on Earth, but space makes the penalty harsher. On Earth, a broken house is still surrounded by air. A failed heater does not remove the atmosphere. A contaminated water line may be repaired, while rivers, rain, and other supply chains exist elsewhere. In space, the environment outside the wall is not a backup. It is the reason the wall exists. That is why every future colony must be judged by a simple question: how many things can go wrong before people die? If the answer is 1, the colony is not safe. If the answer is 2, it is better, but still fragile. If the answer is dozens, and those failures can be detected, isolated, repaired, and survived, then a settlement begins to look less like a camp and more like a real home. This brings us back to the solar system itself. A safe solar system is not one without danger. That kind of solar system does not exist. It is one where dangers do not all become existential at the same time. It is one where no single asteroid can end civilization. No single solar storm can destroy all infrastructure. No single planet can hold every human being, and no single failure can erase memory, industry, and life. That kind of safety is possible only through design. The universe does not provide it automatically. Another part of the galactic environment is stranger, because it arrives not as radiation, but as visitors. The solar system is not the only system that loses objects. Comets can be thrown away. Asteroids can be ejected. Planets can be kicked into darkness. During the chaotic birth of star systems, gravity behaves like a crowded room. Young planets pull on one another. Giant worlds scatter smaller bodies. Close encounters can sling objects outward until they are no longer bound to their original stars. That means interstellar space is not perfectly empty. It contains travelers. Most are probably small, cold, dark, and almost impossible to see until they pass close to a star. Some may be comet-like. Some may be rocky. Some may be fragments of planet-building material from other systems. A few could be much larger. The discovery of interstellar objects passing through our solar system changed the feeling of the space between stars. It showed that material from other systems can cross our neighborhood, briefly entering the domain of the Sun before leaving forever. For Earth, a passing interstellar object is not automatically more dangerous than a local asteroid. Most will miss everything. Space is large, but they create a different detection problem. They can approach on unusual paths. They are not regular members of the solar system. Their speeds may be high enough that warning time is shorter and deflection harder. They are reminders that the Sun's family is not closed to strangers. A future civilization spread across the solar system would need to watch not only the known orbits inside the Sun's gravity, but also the open lanes from outside. The sky is not just a dome of stars. It is traffic. Most of that traffic is invisible until light catches it. Then, there are rogue planets. A rogue planet is a world without a star, traveling through the galaxy alone. Some may have formed directly from collapsing gas. Others may have been expelled from planetary systems. They are hard to detect because they do not shine like stars. They may be found when they bend the light of background stars through gravitational microlensing, or if they are young and warm enough to glow faintly in infrared. A rogue planet passing near the inner solar system would be extremely unlikely on human timescales. But the point is not that one is waiting just outside Neptune. The point is that the galaxy contains massive wandering objects, and gravity has long memory. A close enough passage by a large body, even far from the planets, could disturb distant small objects, alter comet paths, or change the outer architecture over long periods. The solar system's safety depends on the absence of strong disturbances. The galaxy does not guarantee that absence forever. Even when nothing large passes nearby, the solar system carries its own deep time instability. The planets look orderly because the present arrangement has lasted long enough for life to evolve and for astronomers to measure it. But stable does not always mean perfectly predictable forever. In a simple drawing, the planets move in clean ellipses around the Sun. In reality, they tug on one another. Jupiter pulls on Saturn. Saturn pulls on Uranus. Venus and Earth exchange small gravitational influences. Mercury, the smallest inner planet, is especially sensitive to long-term changes in its orbit. The entire system is a many-body problem, and many-body systems can show chaotic behavior over very long times. Chaos here does not mean the planets are about to fly away next week. It means tiny differences in initial conditions can grow across immense timescales, making exact long-term prediction impossible beyond a certain point. The solar system can be stable in the practical sense and still mathematically chaotic in the deep future. This is another reason safe forever is too strong. The planets are not gears in a perfect clock. They are worlds in a gravitational conversation. Most simulations show that the solar system remains broadly stable for a very long time. That is good news. But some rare scenarios show that inner planet orbits can become more extreme. Mercury's path can shift. Interactions can grow. In the most extreme possibilities, inner planets could experience dangerous close approaches or collisions, though such outcomes are not the expected day-to-day future. For the purpose of human civilization, this may feel irrelevant because the timescales are so large. But for the question in the title, it matters. Forever is a severe word. The longer the clock runs, the more small probabilities deserve attention. The solar system is not an unchanging sculpture. It is a moving system that has already changed dramatically. The early solar system was violent. Planets migrated. Small bodies were scattered. Moons were captured or destroyed. Giant impacts shaped worlds. The asteroid belt was depleted. Comets were sent outward. The moon itself likely formed from a colossal collision in Earth's early history. The calm arrangement we see now is not how the story began. It is a temporary chapter after chaos. That history matters because it warns against thinking the present arrangement is the natural final form. The solar system has reorganized before. It can be disturbed again, even if future changes are slower and rarer than the violence of its youth. There is also a danger from inside civilization itself. At first, this may not sound like a solar system problem. Human conflict, bad decisions, careless engineering, and short-term thinking seem social rather than astronomical. But once civilization spreads beyond Earth, human systems become part of the solar system's safety problem. A mining operation can change an asteroid's path if done carelessly. A powerful propulsion test can create debris. A failed nuclear system in orbit can contaminate a region. A conflict between settlements could target life support infrastructure. An automated industry that replicates too aggressively could create hazards in space lanes. A network of satellites, stations, mirrors, fuel depots, and habitats can become a new environment that must be managed. In other words, humans will not only survive hazards, they will create some. This is not a reason to avoid space. It is a reason to treat expansion as responsibility rather than conquest. A civilization that enters the solar system with the mindset of using everything quickly may make the system more dangerous. It could fill important orbits with debris, damage fragile sites, destabilize small bodies, or build systems that are efficient but brittle. The first great safety challenge may not be surviving Jupiter, comets, or solar storms. It may be learning not to turn the solar system into a larger version of every mistake made on Earth. Space looks endless, but useful space is not endless. Stable orbits matter, launch windows matter, ice-rich locations matter, safe landing zones matter, radio-quiet zones matter. Caves, lava tubes, polar craters, asteroid resources, and low-energy transfer routes may all become valuable. If those places are damaged, crowded, politicized, or poorly managed, the solar system becomes less safe for everyone who depends on it. A future lunar economy could make the moon more useful, but it could also cover key areas with dust, debris, abandoned machines, and competing claims. A future Mars program could build real independence, but it could also create fragile settlements that require constant rescue. Asteroid mining could provide metals and water, but it could also alter orbits in ways that require strict control. Large solar power structures could help civilization, but they would need careful protection against collision, sabotage, and cascading failures. This adds a human layer to the natural hazards. The solar system may not be safe forever, partly because nature changes. It may also become less safe if intelligence expands faster than wisdom. That is not poetic language. It is operational. More machines in space means more possible failure modes. More settlements means more dependencies. More energy means more consequences when systems go wrong. A civilization that can move asteroids must also be able to prevent asteroids from becoming weapons or accidents. A civilization that can build habitats must learn how to rescue them. A civilization that can live in orbit must learn how to keep orbital regions usable for centuries. The solar system is not only a destination, it is infrastructure waiting to exist. And infrastructure can decay. This is one of the least dramatic but most realistic futures. Not one explosion, not one asteroid, not one giant cosmic event, but slow decay, habitats losing maintenance, archives becoming unreadable, power grids failing, spare parts running out, launch systems becoming too expensive, political cooperation fading, and once promising colonies turning into isolated survival sites. A solar system civilization would have to fight entropy in practical form. Dust on panels, leaks in seals, metal fatigue, radiation damage, software rot, lost skills, forgotten procedures, supply routes that no longer operate. A station does not remain safe because it was built well once. It remains safe because generations keep understanding it. That may be harder than building the first habitat. A launch can be celebrated. A colony can be announced. A base can be filmed. But long-term safety is quiet maintenance, repeated again and again after the excitement has passed. This is why some of the most important people in a future solar system would not be heroic explorers. They would be technicians, farmers, doctors, archivists, teachers, inspectors, recycling engineers, radiation specialists, people who notice small failures before they become final ones. A safe solar system is not made only by reaching new places. It is made by keeping places alive after arrival. The deepest danger, then, may be the mismatch between cosmic time and human attention. Space requires plans that outlive careers, companies, governments, and trends. A comet may need watching for decades. A power system may need replacement after many years. A habitat may need maintenance across generations. A world may need terraforming plans measured in centuries, if such work is ever attempted at all. Human attention is short. The solar system is not. That gap can be deadly. A civilization can know what to do and still fail to keep doing it. It can build warning systems and then underfund them. It can design backups and then remove them to save money. It can spread to other worlds and still neglect the boring systems that make those worlds livable. It can win the first stage of space expansion and lose the long maintenance phase afterward. This is why the title does not say the solar system is unsafe now. It says it may not be safe forever. Forever includes boredom. Forever includes decay. Forever includes politics, budgets, memory, culture, accidents, and the slow forgetting of why protection was built in the first place. There is another future danger that feels almost too distant to matter, yet it matters because it is certain, in a way many other hazards are not. The sun will change. Not suddenly. Not in a human lifetime. Not in a way that makes tomorrow's sunrise suspicious, but slowly, steadily, as stars like the sun evolve. The sun is not a fixed object. It is a nuclear engine working through fuel. Over time, its internal balance shifts. Its brightness changes. Its future is not a matter of if, but when. Long before the sun becomes a red giant, Earth may face a habitability problem. As the sun grows gradually brighter over geological time, the conditions that allow liquid water to remain stable on Earth's surface may become harder to maintain. The climate system is complex, but the general direction is not comforting. More solar energy means more stress on the balance that keeps Earth temperate. Oceans, clouds, carbon cycles, weathering, greenhouse gases, and planetary feedbacks all matter. But a brighter sun pushes the system. Eventually, the habitable zone moves outward. Earth does not move with it. This is one of the quietest and most serious threats in the entire video. It is not a rogue planet. It is not a black hole. It is not a comet blazing out of the Oort Cloud. It is the normal aging of the star that made Earth possible. The same sun that warmed the oceans will one day warm them too much. The same light that feeds life will one day become a pressure on life. This is not betrayal. It is stellar evolution. For most of human culture, the sun has been treated as the symbol of stability. It rises, it sets, it returns. It marks days, seasons, harvests, calendars, and life itself. But astronomy changes that picture. The sun is stable enough for civilization. It is not eternal enough for forever. That difference is enormous. A civilization that thinks in centuries may never need to confront it. A civilization that wants to survive for millions or billions of years must. At first, the solution may seem simple. Move outward. Mars, the moons of Jupiter, the moons of Saturn, and habitats farther from the sun may become more attractive as solar brightness changes. Worlds too cold today may receive more warmth later. The solar system's habitable regions may shift with time. But this is not a simple upgrade path. A brighter sun also changes radiation, energy balance, ice stability, atmospheres, and long-term planetary environments. Outer worlds are not waiting like empty houses. Europa is locked under ice. Titan has a thick atmosphere, but brutal cold and strange chemistry. Mars has no thick, breathable air. The gas giants have radiation belts and deep gravity wells. The asteroid belt has material, but not Earth-like shelter. A future civilization might adapt to these places. But adaptation is work. The solar system will not politely rearrange itself into a new Earth. The later red giant phase is even more dramatic. The sun will expand enormously compared with its current size. The inner solar system will be transformed. Mercury and Venus are expected to be engulfed or destroyed. Earth's fate is more complex in scientific models because mass loss and orbital changes matter, but the planet's surface would not remain a familiar living world. Even if Earth were not swallowed whole, it would be scorched beyond recognition. By then, the question is no longer whether Earth is safe. It is whether Earth is still a place life can belong. This is the deepest reason the solar system may not be safe forever. The threat is not only that outside events can harm it, the threat is that its central star is evolving. No planetary defense system can stop the sun from aging. No asteroid deflection mission can keep the habitable zone fixed. No emergency shelter can preserve Earth as it is across stellar time. The only answer would be movement. Not a temporary evacuation, a long migration. Perhaps outward through the solar system, perhaps into artificial habitats, perhaps to other stars, perhaps into forms of life and civilization we cannot yet describe. But if survival is measured on the deepest timescales, remaining exactly where we are is not a permanent strategy. This does not make the present meaningless. It makes the present rare. We live during a long but temporary interval when Earth is comfortable enough for open skies, liquid oceans, forests, cities, and unprotected breathing. We live while the sun is calm enough for life but bright enough to sustain it. We live before the inner solar system has been rewritten by stellar aging. That calm interval can feel permanent because human lives are short. Astronomy says otherwise. The solar system is safe enough for now. It is not safe forever. That phrase becomes more serious the longer we follow it. At first, it sounds like a warning about asteroids. Then, it becomes a warning about solar storms. Then, about comets from the Oort Cloud. Then, about passing stars, cosmic rays nearby supernovae, fragile colonies, and eventually the sun itself. Each layer extends the idea of danger farther outward and farther forward. By the end, safety is not a place. It is a process. A civilization that wants to survive must keep learning, watching, building, repairing, and moving. It must build telescopes before impacts. It must harden power grids before storms. It must learn to live beyond Earth before Earth becomes too stressed. It must create habitats that are not entirely dependent on one planet. It must preserve knowledge across disasters, and it must avoid turning every new world into a copy of the same fragile system. That may sound enormous. It is. But the solar system also gives us tools. It gives us the Moon as a nearby test of living off Earth. It gives Mars as a world difficult enough to teach survival, but close enough to imagine reaching. It gives asteroids filled with metals and volatiles. It gives comets and icy bodies that preserve ancient material. It gives the outer moons, giant planets, solar energy in the inner system, nuclear fuel possibilities, gravity assists, and millions of natural laboratories. The same solar system that is not safe forever may become the training ground for lasting beyond it. This is the strange balance. Danger and opportunity are not separate here. They are the same landscape viewed from different distances. Asteroids can threaten Earth, but they can also teach us how to move objects in space. Solar storms can damage technology, but they also teach us how to read the sun. Lunar dust can destroy machinery, but learning to handle it teaches us how to build on airless worlds. Mars can trap humans, but trying to survive there teaches closed life support, local resource use, and planetary-scale caution. The Oort Cloud can send comets inward, but studying it teaches the history of the solar system and the influence of the galaxy. Every hazard is also a lesson, only if we pay attention early enough. There is one more layer that often gets ignored because it does not look like a disaster at all. Information. A civilization can survive a storm, an impact, or a failed settlement, only if it remembers enough to recover. Knowledge is not weightless in the practical sense. It has to be stored somewhere, it has to be copied, it has to be readable after machines change, languages change, power systems fail, and institutions disappear. If humans spread through the solar system, safety will depend not only on oxygen tanks and radiation shelters, but on memory. A lunar base without repair manuals is fragile. A Mars city without medical knowledge is fragile. An asteroid habitat without orbital records is fragile. A shipyard without manufacturing standards is fragile. A telescope network without archives is half-blind. This matters because the dangers of the solar system are not always defeated by strength. Many are defeated by continuity. If one generation finds a dangerous asteroid, the next generation must still track it. If one century builds a warning system for solar storms, the next century must still maintain it. If one colony learns how to recycle water without losing trace nutrients, the next colony must not forget the lesson. Space punishes broken chains of knowledge. On Earth, forgotten skills can sometimes be rebuilt from the environment. A person can learn to farm because soil, rain, air, and sunlight are still available. A lost tool can be replaced with another method. A broken road can be bypassed. In a closed habitat, forgetting is more dangerous. The environment does not forgive ignorance. A tiny mistake in air chemistry, crop cycles, radiation shielding, or microbial balance can become a life support problem. So the safety of the solar system may depend on libraries as much as rockets. Not just digital libraries, because digital systems fail. Not just printed books, because books decay and may not include working machinery. Not just experts, because experts die. A long-lived civilization would need layered memory. People trained in essentials, archives stored in many places, simple instructions for rebuilding critical systems, durable records, machine-readable databases, and cultures that treat maintenance knowledge as sacred rather than boring. That word may sound strange in a science documentary, sacred, but in a spacefaring civilization, a water recycler may be as important as a cathedral. A greenhouse may be as important as a monument. A radiation shelter may be as important as a palace. The things that keep people alive must be protected from neglect, not only from accidents. There is also biological memory. Earth's biosphere is the only living system we know. If humans spread outward while Earth remains the only complete living world, then every off-world habitat carries only a tiny sample of life's diversity. Seeds, microbes, animals, human genetics, soil systems, fungi, algae, plankton, and countless ecological relationships cannot be replaced easily, once lost. A future solar system may contain many settlements and still preserve only a narrow version of Earth life. That would be safer than having everything on one planet, but not safe enough. A true long-term civilization would need biological backups distributed across distance. Seed vaults on Earth are a beginning, but a multi-world future would need deeper redundancy. Frozen embryos, microbial libraries, crop diversity, soil organisms, medical cultures, genetic records, and living ecosystems would have to be protected in different places under different conditions. This is not only sentimental, it is practical. A colony with one crop system is vulnerable. A habitat with a narrow microbial ecology is vulnerable. A settlement with low genetic diversity is vulnerable. A civilization that loses pollinators, medicines, or key organisms may discover that life support is not only metal and electricity. It is biology organized carefully enough to keep renewing itself. The solar system may not be safe forever if life remains concentrated. It becomes safer when life is copied, diversified, and understood. But copying life is harder than copying data. A seed vault does not equal a forest. A DNA file does not equal an ecosystem. A tank of algae does not equal an ocean. Every living system has relationships that are difficult to compress. Water chemistry, temperature, light cycles, nutrients, microbes, waste, disease, and reproduction all interact. This means the future safety of humanity may require a new kind of ark. Not a single ship escaping one disaster. Many arks spread through many places, carrying different parts of Earth's living memory. Some may be underground on the Moon, some may be buried under Martian regolith, some may orbit in cold storage, some may float inside large habitats where real ecosystems are maintained, not just preserved as samples. Some may be sent farther out, away from the inner solar system, as insurance against threats near the Sun. The purpose would not be to abandon Earth. It would be to stop making one world hold every copy of the story. Even then, the problem is not solved. Backups must be refreshed, genetic material degrades, power systems fail, cultures forget why archives matter. Machines designed to preserve life can become tombs if no one maintains them. So the future of safety becomes a future of repetition. Check the seals, test the pumps, update the maps, refresh the archives, train the children, watch the sky, store the seeds, repair the mirrors, clean the panels, read the old warnings. In a movie, survival is a dramatic escape. In the real solar system, survival may look much quieter. It may look like people doing unglamorous work across centuries because they understand that a civilization is not protected by one heroic mission. It is protected by habits that continue after heroism fades. That is not a small idea. It may be the difference between a species that briefly visits space and a species that belongs there. There is also the problem of perspective. A civilization can become very good at surviving one kind of danger and still remain blind to another. Planetary defense focuses attention on rocks. Space weather focuses attention on the sun. Climate science focuses attention on Earth. Deep space engineering focuses attention on life support and propulsion. Each field is necessary, but no single field contains the whole future. The solar system is a connected system. A solar storm can affect communication with a Mars crew. A launch failure can delay repairs to a lunar habitat. A damaged satellite network can weaken asteroid tracking. Political conflict on Earth can interrupt supplies to people far away. A dust storm on Mars can become a power problem, which becomes a food problem, which becomes a medical problem, which becomes a rescue problem. The danger is often not the first event. It is the chain after it. That is why future safety will depend on systems thinking. A hazard map is not enough if the response system is fragile. A colony is not safe if its backup depends on the same failure that damaged the primary system. A warning is not useful if no one has authority to act. A rescue plan is not real if the vehicles, fuel, crew, and launch window do not exist when they are needed. In space, preparation has to be physical. It must be built before it is required. The most dangerous future is not the one where the solar system contains threats. It always has. The most dangerous future is the one where civilization remains surprised by things it could have known were possible. A civilization that never looks for asteroids will be shocked by an impact. A civilization that ignores space weather will be shocked by a solar storm. A civilization that builds colonies without independence will be shocked when supply chains fail. A civilization that assumes Earth will stay perfect forever will be shocked by planetary change. A civilization that treats the sun as permanent will be shocked by stellar evolution, even if that shock comes very far in the future. Preparation is not fear. It is respect for time. And time is the one thing the solar system offers in large amounts, at least for now. We have time to map the skies, time to study the sun, time to practice deflection, time to build stronger technology, time to learn closed ecosystems, time to place telescopes in better positions, time to explore the moon, Mars, asteroids, and the outer planets. Time to decide whether we want civilization to be a temporary episode on one planet or a longer story spread through many places. But time has a way of feeling infinite until it is gone. That is why this subject is calm and terrifying at the same time. There is no alarm bell ringing every morning. There is no giant countdown visible in the sky. Earth still turns. The sun still rises. Jupiter still circles in the distance. The moon still pulls the tides. The planets still keep their ancient paths. But underneath that calm, the system is moving. Asteroids cross orbits. Comets wait in darkness. The heliosphere breathes against the galaxy. The sun changes slowly in its core. Stars pass at great distances. Radiation flows through space. Planets perturb one another across deep time. Human technology becomes more powerful and more vulnerable at once. The solar system looks like home because it is home. It looks safe because, for our kind of life, during this particular era, it has been safe enough. But safe enough is not the same as guaranteed. A house can stand for centuries and still need repair. A ship can cross an ocean and still require maintenance. A city can survive storms and still plan for the next one. A civilization can grow under one star and still eventually need to understand that the star is not a promise. That may be the final meaning of the solar system's future. It is not a trap, but it is not a cradle forever either. It is a temporary region of relative calm inside a much larger universe. It gave Earth the conditions for life. It gave intelligence time to appear. It gave humans enough stability to look upward and realize where they are. But if that intelligence wants to last, it cannot confuse the cradle with the whole future. The solar system may not be safe forever. Not because it is hostile in every moment. Not because disaster is waiting tomorrow. But because everything that protects us has limits. Earth has limits. Technology has limits. Orbits have limits. The heliosphere has limits. The sun has limits. Even a beautiful, familiar system can change when enough time passes. And maybe that is what makes our situation so rare. We are alive during the interval, when the solar system is still gentle enough to let us think, but dangerous enough to teach us urgency. It is quiet enough to feel peaceful, but not permanent enough to justify complacency. It is close enough to explore, but large enough to humble every plan we make. If we stay careless, the solar system remains a place where safety can end by surprise. If we learn, it becomes something else. A warning, a workshop, a map, a first step. The future will not be made safe by believing the present will last. It will be made safer by understanding why it will not. And perhaps, one day, if humans survive long enough, the solar system will no longer be the edge of our story. It will be the place where we learn the most important lesson a young civilization can learn: that home is not safe because the universe protects it. That is the quiet duty behind every future dawn and every world we build. Home is safe only for as long as we learn how to protect it back.